All right, ladies and gentlemen, so we're recording right now. So, last time we hung out, we spent a lot of time focusing on identifying what ions we're going to form, what charge they're going to have, excuse me, and identify which one was the cation, which one was the anion. That's what we spent a lot of time doing. Now we're getting to the point where we're starting to write our formulas. So we have a 4-step process to do this. Our first step process is one, we're going to write the symbol and charge of our positive ion, also known as our cation, our metal. First thing we're doing, so if my example here is magnesium and chlorine, first thing I'm going to write is magnesium. Magnesium is in group 2, it's number 12 on my periodic table, therefore it has 2 valence electrons, therefore it's going to lose both of those valence electrons to give me a magnesium plus 2. Step 2, I'm going to write the symbol and charge of the negative ion, the non-metal anion. Chlorine is our second halogen, right under fluorine. Remember, cations, our metal ions, always shed those valence electrons. Our anions want enough valence electrons to get to the next noble gas. Chlorine's in group 17. It gains 1 more electron. It has the same electron configuration as argon, and that's the most stable position for chlorine to be in. So, Cl minus 1, as you see on your screen. Now here's the thing. Step 3, determine the ratio that balances and cancels charges. Meaning that my total positive charge has to equal my total negative charge. I start off with a plus 2 and a minus 1. Does 2 equal 1? They don't. So that means I need to have another negative charge to balance out the 2 positive charges. So I get a second chlorine. And from there, now my positive charge 2 is balanced out by 2 negative charges. Step 4, I write the chemical formula without the charges, and I use the subscripts to show how many of each ion I used. And the subscript, that's just the number at the bottom of the letter. Remember, subscripts down here, superscripts up top. So that's how we get magnesium chloride is MgCl2. I want to do a couple examples with you. I'm going to push this up. So if I want to do a couple examples, let's do 3 of them real fast. Let's do lithium and oxygen. Lithium and oxygen. Give me a quick second here. Let's grab this. I slide this right down. There we go. If I want to do lithium and oxygen, there we go. My first step is to write the symbol and charge of the positive ion, the cation, the metal. So I know lithium, between lithium and oxygen, lithium is in group 1. I know lithium is the metal. So what is the ion for lithium? Li plus 1, plus 2, plus 3, plus 4. What's lithium's ion going to be? Plus 1. Li plus 1. Everybody agree with that? Pam, you got your notes? Okay, I'm just checking. Step 2, I need to write the symbol and charge of the negative ion, my anion, the non-metal. What is the ion for oxygen? It's going to be what? -2. Because remember, oxygen is in group 6A, also known as group 16, where it only needs 2 electrons to get that outermost shell. So, step 3, determine the ratio that balances and cancels the charges. So I see here, does 1, +1, equal 2? Does 1 equal 2, guys? No. So what do I have to add in order to get to balance out this ratio? Do I need to add more lithium or more oxygen? Was it? I got to add more lithium, right? I got -2 over here. I got +1 over here. So now I have 2 positive charges and 2 negative charges, right? 2 equals 2. I've balanced out my charges. Step 4, I rewrite my chemical formula without the charges, using the subscripts to show how many of each ion I used. So in this situation, LiO, how many lithiums did I use? 2, right? 1, 2. Li2O. I want you to do, grab your whiteboards for this one. Should be markers in the boxes. I want you to do sodium and chlorine. Sodium and chlorine. I want you to write that on your whiteboard. So make sure you pass the whiteboards out. Make sure you grab a marker. Yeah, go ahead, grab the pens. There you go. What's up? That's trash. You're not writing it down for you're giving me the ion, so you're getting into the A. As soon as 3:20 guys, my winter breaks like the exact same time. So I gotta fight the action. Today. Give me 1 second. All right. So give me 1 quick second, guys. Let me get Katya set up. Katya, do me a favor. Meet me at the front, okay? Extra periodic table to stay in the bench. Extra periodic tables? There's no way we're going to have periodic tables. We don't have periodic tables. Oh, no, they're right here. They're hiding from me. Okay. All right. So, do me a favor, guys. Show me what you got on your board so far. Let me see what you got. Lift them up in the air. It's okay if we didn't quite get it. We're going to review it. That's the whole point. All right. Okay. All right. So, let's talk about it. All right. So, if I'm looking at my periodic table, I know, just because I've also beaten this into my head plenty of times, and I keep seeing sodium come up over time, I know to know it's Na. If you don't know sodium's Na, it's okay. That's why we write also the regular name underneath it. So I know I need Na, and chlorine, look at my periodic table, is Cl. All right, so step 1, I need to write my metal, and I need to determine what charge sodium's going to get. Is sodium the metal or non-metal in this relationship? It's the metal, right? How many valence electrons does sodium have? Has 1, right? It's in group 1. Everybody in group 1 has 1 valence electron. We agree with that? We know that group 2, they all have 2 valence electrons. When I look over in group 13, also 3A, 3 valence electrons, 14, 4, 15, 5, 16, 6, 17, 7, and 18 has 8 valence electrons. We agree with this, right? We all feel comfortable with that bit of knowledge, yes? Perfect. So, in an ionic bond, my metals want to lose that valence electron. So that's going to give my sodium a positive charge. My protons will now outnumber my electrons. What charge are we putting on the ion? Is it going to be a +1, a +2, a +3, or a +4? +1, because we're losing just 1 valence electron, right? So it's sodium +1. If we take a look at our protons, if we take a look at our charges, we have 11 protons. If I lose 1 electron, I now have 10 electrons. Minus that, +1. Sodium's going to have a +1 charge for an ion. my cation, my positive ion, is going to be a +1 for sodium. Chlorine, on the other hand, is on the other side of my steps. Remember, on the left-hand side of my steps, all of these are metals. Of course, my pen's dying. And everybody on the opposite side of the steps that's not sitting on the steps are my non-metals. So, if my metals always lose their electrons, what are my nonmetals doing? Are they also losing or are they gaining electrons? They're gaining. And they're only going to gain as many electrons as they need to get to that magical noble gas configuration. Chlorine is off by 1 electron. Chlorine only needs 1 electron to be happy. So that's where we get Cl minus 1, because I'm adding an electron. Chlorine normally has 17 protons. And in a neutral state, we'll have even amount of electrons. So it'll be 17, but we're adding an electron, so it's 18. My second number is bigger than my first number. Therefore, my answer is -1. Now, big thing. So we've identified our charges. Now we need to look at step 3, where I need to make sure that my charges equal each other. My positive charges equal my negative charges. 1, 1. Do they equal each other? Does 1 equal 1? Absolutely. So it means I write NaCl. Let's do one more. Let's do aluminum and oxygen. Let's walk through this one together, okay? Aluminum, I know is Al on the periodic table. What cation is formed from aluminum? Al +1, +2, +3, or +4? +3. Why? Because aluminum is in group 13. Right here we find aluminum, means I have 3 valence electrons I can get rid of, right? Aluminum's going to lose all 3, +3. Oxygen. Oxygen forms which anion? -1, -2, -3, -4. -2. So I've done step 1. I've written out my cation. I did step 2. I wrote out my anion. Now I'm on step 3. I got to make sure that my charges equal each other out. On the metal side, I got 3. On the non-metal side, I got 2. Does 3 equal 2? No. I gotta add some elements there. I gotta add some atoms. Which one am I going to add first? Am I going to add aluminum or am I going to add more oxygen here? More oxygen? Sure. O -2. Now it's 3 equals 4. Does 3 equal 4? No. I got to keep adding. Who else am I going to add? What do you want to add? You want to add another? You want to add another aluminum? You want to add another oxygen? Sure, let's add an aluminum. Al plus 3. So now I have 6. Does 6 equal 4? No, right? What else am I going to add? Am I going to add another aluminum or we're going to add another oxygen? Another oxygen, right? O minus 2. Does 6 equal 6? ALO. How many aluminum atoms did I use? How many? I added 2, right? 1, 2, right? 2 aluminum ions were used in this. How many oxygen ions were used? 3. Al2O3. It's important when we're making ionic bonds to know a couple things. What's forcing our ionic bonds to stick to each other? Because my ions are oppositely charged and they're next to each other. They're going to stick together. This is the biggest thing. I put a star beside this. I make sure you write that out. When they join together, they must have a ratio that allows their charges to cancel out. When we looked at sodium chloride, +1, Cl minus 1, 1 equals 1, therefore NaCl. Calcium is in group 2, Ca plus 2, Cl minus 1. I don't, 2 and 1 do not equal each other, therefore I need another one. Now I have 2 equals 2, Cl, Cl2. The charges have to cancel each other out. It's a big thing. So now I'm going to give you guys a chance to try on your own. I want to do the barium and bromine one with you so you guys got a head start on it. But I want you guys to do the other 3. From looking at my periodic table, my cation, barium, what's its ion going to be? +2, so Ba +2. What about bromine? Give you a hint, bromine's one of the halogens. -1. -1. So Ba +2, Br -1. So now we got to think of the formula. Excuse me. When you think of the formula, remember, my charges have to equal each other. I got 2 and I got a 1. Does 2 and 1 go into, does 2 and 1 equal the same? No. So what do I need to add? Do I need to add more barium or more bromine? How many more bromines? 1. So I need 2 altogether. So my formula for barium and bromine is Ba Br2. I would like for you to work on the other three.
So, without non-metal, full electrons, technically there's no mass. If I have a file with electrons, how many electrons are needed to be? Yeah, so the gaining electron minus. So here, 1, 2. My nominal is always gaining electrons. Check to see what else is there. Be careful about your calcium phosphorus. Get your formula a little backwards. There, see what you have. It's nice run. What do you got so far? Hey, I think the first one is here. No, you're fine. He, Justin was a little bit backwards.
We'll talk about that in a second. The charge to your right, this is formula was off. You got your numbers backwards. It's not 2, 3, it's 3, 2. All right. So, lithium. Lithium is Li plus what? Li plus 1. Nitrogen is N what? Minus 3. So in this situation, I have minus 3, I have 1. I need 2 more lithiums to balance out to 3 against nitrogen's 3. So my formula, Li3N. Strontium. Strontium is in group 2. Sr plus what? 1, 2, 3, or 4? 2. Oxygen minus 1, 2, 3, or 4? 2. They balance each other out, right? 2 equals 2. SRO. Calcium. Ca2 plus 2. Phosphorus is what? Minus 3. So, I hope you had this one a little backwards. If I add another calcium, I now have 4 equals 3. Is that right? No. Ca plus 2, P minus 3, 1, 2, 4, 6 equals 3, 6. Ca3, P2. That's what we were looking for. The classwork that we're going to be taking a look at in a second is about this. The homework that you're going to be doing is about this. Now I only have one last thing I want to talk about before we get into the classwork / homework, and that is the properties of our ionic compounds. First thing we want to point out is that our ionic compounds always form this crystal lattice structure. And we can break that down. We can see that as Cl, Na, Cl, Na, Na, Cl, Na, Cl, Cl, Na, Cl, Na. They form this repeating structure. Now it's hard to see here, but in my image, I have a bunch of cubes of salt. Now, what we're going to find out in a second is that regardless of how big my salt cubes are, if I'm looking at salt, let me do this. If I'm looking at, I think I can zoom in with this, or I'll see if I can or not. If I'm looking at salt, either in a very tiny form, can I zoom in? That's exposure. Oh, well, let me zoom in. All right, so I gotta bring it up closer. Try to see if I can get this to work a little bit. Because I can't zoom in while I'm recording. Kind of hard to see it. But we see small little cubes. But if I go and take a look at a big old chunk of salt, we have a mineral named halite that is nothing more than just giant block of salt. I get the same situation. I get these flat sides. I get these flat cubes. I get a bunch of squares. I get squares. And if I take my hammer, which I'm going to pull my camera back for a quick second. Oh my goodness. And I break my block up, I get the same situation where I get these flat lines. All my flat lines, give me a second, let me pull this back up, of where it breaks. These flat surfaces. I'm going to pass out those who are here, let you guys go ahead and take a look at our good buddy halite, which is just salt in large block form. And you can see that for the most part, it's fairly flat, especially where I broke it. I think someone's out right now. Nyla's out right now, looks like. When she goes back, you're more than welcome to. But I see these flat surfaces form. Go ahead, pass them down so everyone gets a chance to take a look at it. This is a common structure, a common effect when we look at our ion compounds. Actually leads us to one of our properties. Now, the question is, why? Why does that happen? Why does it form these flat surfaces? Because if I was so I have my drawing, and I smash my hammer down here. So I got my hammer. It's smashing into these bonds here. It's going to force this group to slide down one. So now it's Na, Cl, Na. So now I have sodium next to sodium. Two positive ions next to each other. Do my ions want to be positive and positive right next to each other? Do my magnets like to be positive and positive right next to each other? No, they're going to repel against each other. Same thing with my chlorine. Does my chlorine want to be close to each other? No, they're going to repel again. So we're going to see that whenever we see ionic bonds, they're always brittle. So the last thing I want us to take a look at Nope, not that one. That one we're not doing. Is the last bit of my properties. There we go. Last bit, my other physical properties of our compound, of our ionic compounds. One thing we're going to notice is that our ionic compounds are always room temperature. Always room temperature. Always solid at room temperature. Our salts, we have some bunch of different types of ionic compounds that we're going to take a look at in the lab that we're going to do, like baking soda, Epsom salt, regular table salt, a couple other things. It's always solid at room temperature. It's also very hard to melt or boil. When you put seasoning, when you put salt on your meat before you cook it, you notice that the salt doesn't melt on the surface of the meat. Why? Because table salt, pure table salt, has a boiling point around 1400 degrees Celsius or around 2500 degrees Fahrenheit, depending on which system you use. Most ovens in the United States, conventional ovens that you get at the grocery, store, that you use to cook your meals, goes to a temperature of around 500-600 degrees for broil. Nowhere near the temperature needed to melt salt. They are incredibly stable due to those strong intermolecular forces that hold it together, that makes it form that pattern. The crystals of any given compound will be the exact same shape. If I could zoom in better on my table salt, I would see that's in cubes. When I showed you a nearly pure mineral of halite, excuse me, it was in cubes. They're not the best cubes, but they were in cube-like shape. I would not smell it. It's not going to smell anything. And please don't lick it. 1, yes, it's salty. 2, my hands and everybody else's hands before you has been on it. So if you're licking the salt, who knows where their hands have been? Ionic compounds are brittle. If you hit them with a hammer, we can break it, as we clearly saw. And in a second, we're going to see that they're going to conduct electricity if they're molten or dissolved. Now here's where I'm going to pull out a little quick video. So, with already seeing that, I want to jump into the classwork/homework so we get a head start on it. And we might get a head start into the lab that we're going to do today. So I'm going to come around, I'm going to pass out Ionic bonding worksheet. We're going to do 1 or 2 of them together, and you're going to finish the rest for homework to kind of help us work our way through these questions. It's possible. It is possible. All right. So, keeping us primed and going, we have the Ionic bonding worksheet. If you know the name of a binary compound, you can write its chemical formula. That's all we're doing today. We're working on writing our chemical formulas. The next paragraph kind of details exactly what we did beforehand. We went through those 4 steps. 1, start with writing the metal ion and its charge, followed by the non-metal and its charge. Because the overall compound is electrically neutral, decide how many of each ion is needed in order for a positive and negative charges to cancel each other out. When bonds form between positive ions and negative ions, the charges must what? What must the charges do, guys? It's literally in the paragraph I just read. Cancel each other out. Remember how we had the calcium with the +2 and the chlorine with the -1. In order to cancel each other out, I had to add another chlorine to match the 2 positive on the calcium, and now I have 2 -1s chlorines, CaCl2. So if I'm looking at number 2 here, fill in the following table, the examples, and fill in the following table like the example in the top row. Remember to think, good Lord, I can't speak today. Think through the material from the table on the other side of the page while developing your ions. Charges. So my example is sodium and sulfur. Sodium gets a +1 because it's in group 1, it's an alkali metal. Sulfur is just below oxygen, so it gets a -2 because it's in group 16. Now, if I left it like this, 1 doesn't equal 2. I need 2 sodiums to balance out the S-2. 2 Na2, 1 S. I'd like to do barium and selenium. Barium, Ba. What is its cation? +1, +2, +3, or +4? +2. It's in group 2. Therefore, it loses the 2 valence electrons. Selenium, number 34 on the periodic table. How many electrons does selenium need to form the anion? 2. Se-2. Do my 2 charges balance out? They do, right? 2 equals 2. BeS. Beryllium sulfide. I'm going to give you guys a couple minutes. I'm going to give you guys, let's say, 5 minutes. That gives me a little bit of time to set up the lab on my end. I want you to work your way through the page. If you have questions, ask questions. At the end of the 5 minutes, what you don't complete right now, you're going to take for homework. Excuse me. If you get done in the 5 minutes, don't turn this into me right now. Hold on to it in your folder until I see you Friday. Sound good? All right, I'm going to stop recording.